Hello. So now we've reached our final logic gate, the XNOR gate, or the exclusive not or. I've color-coded different elements of this logic gate, and again, in blue we see the or element, in white we see the not element, and in X we see the exclusive element. Um, so it functions just as we might expect it to behave. It's the knotted version of the exclusive OR gate. So you take the result of an exclusive OR, and then you knot that to get the result of an exclusive NOT OR gate. Let's just go through the truth table. We'll breeze through this one really quickly, as it is our last logic gate. So we look at the first case. A is false, B is false. The output of a traditional exclusive OR gate would be false. And so when we knot that, we get true, and that is the output. Second case, we have A is false, B is true. The output for an exclusive OR gate would be true, but when we knot that, we get false. Third case, A is true, B is false. The output of an exclusive OR gate would be true, but when we knot that, we get false. And then for the fourth and final case, we have A and B are both true. The exclusive OR gate would normally yield false here, and then we knot that, so then we have true. And this is the truth table for the exclusive NOT OR. The implementation is exactly what you might expect it, just a NOT. So we would just add our CMOS inverter. That's really it. I just want to take this time and say, with this being our last logic gate, I think I'm really happy to say that now we can move on to some of the more advanced, fun stuff. Because we first built our knowledge of fundamental transistors, very basic ones, the MOSFET P, and I guess I did talk, well, N mainly, but I guess I touched on the P channel transistor. Again, hopefully electron engineering students won't be at my neck for this, for my gross oversimplifications. But yeah, now we understand a little bit about transistors, and using that we were able to create logic gates and show how they physically exist. We created circuit diagrams and we actually played with it, and we got exactly what we wanted. Right? Granted, those weren't the actual implementations, but I have linked you guys resources to look at the actual implementations. And so now we moved from our understanding of transistors to building logic gates, and now we can start using these logic gates to create what I might call higher level reasoning, or more abstract concepts. So hopefully in the next few videos from now on, I won't be using transistors anymore. I'm going to be using logic gates, and again, hopefully it won't, one need not be scared or lost. Anytime you see a NAND gate, we deep down inside we know what it looks like, to a point, right? Depending if you read the resources or not. But even my dummy implementation is an okay attempt at it, right? But anyway, so when we see AND gates, we really know what's going on. Or this is a NAND gate, but yeah. Again, so for the next segment, really what we're going to be doing is, as I described, I said that the NAND gate and the XOR gate were the two universal gates. So the next couple of videos, we're going to reconstruct all the logic gates using only the two universal gates. And then after that, we'll start to use the logic gates. Yeah, so hopefully it'll be fun, guys. This is our last logic gate. I guess we'll be going over them again using the universal gates, but that should be a breeze. And hopefully it'll be fun, guys. Keep learning, and then once we go through the universal logic gates, we can start doing some really fun stuff. Thanks, guys. And I guess I have to repeat it again. Keep learning, guys.